So today we're going to start talking about a different way of solving systems of substitution. So the last time that you had homework, you were graphing what are called systems of equations. A system is when you have two or more linear equations. In this case, we're talking about linear equations. You can have systems of other things too. And those lines, when you graph them on the same coordinates, a couple of different things can happen. One of the things that can happen is you could have a system where you have a line that crosses another line. Okay? And when those lines cross, the place where those lines cross, you get a point of intersection. So that's one thing that can happen. You can get one point where this point is a solution to this line, and this point is also a solution to this line. A second thing that can happen on a graph, you've probably seen it already, is you could get two lines that run parallel to each other. Now, in this situation, you would have no points of intersection. Nothing would overlap, right? And so there would not be any solution to that system because none of the points that are solutions on this line would be solutions to this line. The last thing that could happen is you could have a line, and when you graph the second line, that second line might end up exactly right over the first line and have exactly the same set of solutions. So there's a lot of different things that can happen here. So we're going to talk about possibly figuring out a way where maybe we don't have to graph them all the time. And today's section is called Solving Systems with Substitution. Now, you guys are familiar with substitution. You know that if x is equal to some number, you can put in that x value and then figure out what y is, right? We've done substitution before. It says, given the equation, y equals x plus 4, how can you solve for x and y? Well, honestly, I think you need to know the value of one of the variables, right? You'd have to know. You can't otherwise. How can you determine the value of x if you know y is equal to 8? Well, you would substitute y as 8 and then subtract 4, right? And you'd find x. So how many solutions will you have if there aren't any values for one of those variables? If I don't tell you that x is equal to 8 or y is equal to 8 or x is equal to 0, then we have graphed things that look like y equals x plus 4. And how many solutions are there? There's an infinite number. So if you don't know one of the values of x or y, then there are millions, infinite numbers of pairs of numbers that could fit into that set of equations, into that equation. Okay, so I'm going to ask you to pause right now because you're going to need some colors. You might not need 3, but it would really be a good idea to have at least 2 different colors. Okay, so let's talk about this first system of equations here. We have y equals 6. Remember, y equals c, that's a horizontal line. So we have a horizontal line, and I could actually kind of graph that and see, or kind of get a sense of what's going on in this situation just by doing a real quick drawing here. So I've got this horizontal line, and I have x equals 3y plus 6. If I subtracted 6 and divided by 3, I've got something that's got a negative slope, and it's probably going to be crossing something like that. Okay. Or no, it's not even going to be negative, is it? I take it back. It's just going to have a negative y-intercept. Anyway, so we've got this set of lines. We know they're going to cross somewhere, but I don't feel like graphing them on a real coordinate grid. Instead, what I'm going to do is I'm going to use some color to help you understand what's going on in this problem. I'm going to pick red this time, and everywhere there is a y or something that's equivalent to y, I'm going to underline that in red. So down in this second equation right here, I have a y value. And what I understand is anywhere that there is a y, the value of that y is 6. So I'm going to rewrite this equation. X equals 3 times, and remember the value of y is 6, so we put in 6. And then the rest of the equation says add 6. All right, so I'm going to do this math. X equals 18 plus 6, and I get x equals 24. Well, that was easy, right? I got a value that says that x is 24 when y is 6. Well, that's nice. Okay, so I've got this solution then. It's saying that x is 24 when y is 6. That's the point of intersection. And I did that mathematically. I didn't even have to graph it to find out where they crossed. Now I can double check that, because if I put in 24, 6 into this line, will I find this point on the line y equals 6? Yes, I will, because y is equal to 6. And will I get 24 when y is equal to 6 in the second equation? And the answer is yes, because when y was 6, x was 24. And so I know this is a solution to this equation, the second equation as well. So I can go back and I can check them to make sure that I can verify to see whether or not they're actually solutions to the same, if the same solution works in both equations. So let's move on. Let's look at the next one. This one says y is equal to x plus 4 and x is equal to 3y plus 6. Now there's two ways that I could solve this one. This one's telling me that the y values, again, here we see it right here. This time the y value is worth all of this, x plus 4, right? Y is worth x plus 4. And I see a y in the second equation down here. So let's go ahead and substitute in then in that second equation, just like we did the last time. Look at it's the same system essentially, except the first equation is an x plus 4 now instead of a 6. So x equals 3, and then I have to multiply that by whatever the value of y is. Well, y is going to be substituted with all of this expression. So I have to put that in parentheses because all of that is what the value of y is. And then I go back and I finish off the equation with plus 6 because that's where that came from, plus 6. Okay, so now I'm going to do some math. This is the easy stuff right now. I'm going to distribute 3x plus 12 plus 6 on the end here. I'm going to put together my like terms. I get 3x plus 18. And I need my x's to be together, but they're on opposite sides right now. So I think in the last couple of tests and a couple of times that we've done equations with variables on both sides, I have a sneaking suspicion some of you want to divide by 3, but I can't do that because if I divide this by 3, then I get x over 3. And over here, I'm going to get x. So I'm still going to have x's on both sides. What I have to do is I have to subtract these. I want to get rid of these 3 x's because I want that 18, that constant of 18 to be on the right side all by itself. I want to get rid of this, meaning I want to get that to be a 0 pair. So I got 18 on this side And 1x minus 3x is negative 2x. Divide by negative 2 on both sides, and I get x is equal to negative 9. Well, that's pretty nice. So now I know the x value. Now what I need to do is I need to go and figure out what the y value is going to be then. So I know that these two lines are going to cross somewhere where the x value is negative 9. Now I'm going to take that back and I'm going to put it back in to that first equation, and wherever x is in that first equation, I'm going to substitute back in there. So let's go ahead and do that. So it's two sets of substitution, really. Y equals, and then whatever I said x was worth, which I said was negative 9, plus 4. Plus 4. And y is then going to equal negative 5, right? So that's pretty cool. We just figured out the coordinate pair when x is negative 9 and y is negative 5. These two equations are equivalent, which means they're both solutions to the equations, and that must be the point of intersection, negative 9, negative 5. That's my answer. Point of intersection, right? Okay, we're going to keep working. X equals y minus 8. It didn't go to the next page, my apologies. X equals y minus 8 is the equation that goes with this system and with this system. Now I'm trying to keep it simple. That's why I didn't use a whole huge group of different equations. A lot of these are very similar, you'll notice. The other thing I want you to notice is that substitution is particularly nice when one of the variables is already isolated. For example, they've already solved for x here. They've already solved for y, which means I could also use y to substitute in. So there's no reason why I couldn't work this the opposite direction. I could say, well, y is equal to 3x plus 6, so I'm going to put in 3x plus 6 in place of y in the first equation. Typically, people like to work top to bottom, so I'm just going to stick with that for right now. Let's go. Here's x. All of this has the same value as x, and x is going to fit in here. Let's write the equation. Y equals 3 times whatever we said x was equal to, y minus 8. And then we're going to add 6 on the end, plus 6. Let's do some math. Let's math this up, right? 3y minus 24 plus 6. Combine your like terms. Y equals 3y minus 18. And again, I want that 18 on this side by itself. That negative's going to go with it. I really want to get rid of this 3y again. Minus 3y on both sides. 1y minus 3y is negative 2y. This becomes a zero pair. And I get negative 2y equals negative 18. And if I divide by negative 2, I get y equals 9. Pretty cool, right? So I know that y is equal to 9. I'm going to take that value of 9 and put it in here for y. Okay? So in order to get x, I have to do x equals 9 minus 8. Because I'm just substituting it in place here, right? So x has to equal 1. Awesome. So here's what that means. X is 1, y is 9. So my solution to this system is 1, 9. That is where these two lines will intersect. And I feel like that's a really bad job. Let me rewrite that. 1, comma 9. All right, you go ahead and press pause, and I want you to try the next system. Okay, x is solved for y minus 8. So wherever there's an x here, I'm going to put in a y minus 8. Is this what you did? 3 times y minus 8 plus 6y equals 10. That's supposed to be an equals 10. I think I'm getting a little bit better with this thing, don't you? Okay, so that's equal to 10. Distribute. I get 3y minus 24 plus 6y equals 10. Combine my like terms. I get 9y minus 24 equals 10. Add 24 to both sides. And I get 9y equals 34. Well, this one's not going to come out a really nice number. And if you remember, what I was saying is way back at the beginning of the year when I said, don't bother making this into a mixed number because you're probably not going to want it to be one. Here's that perfect example of why. No pun intended, why. So y is equal to 34 ninths. I'm going to go back up here. I'm going to plug that in. And x is going to equal 34 ninths minus 8, right? Well, that means x is equal to 34 ninths, and I have to make 8 into ninths. 8 is the same as 72 ninths. So x is equal to negative 38 ninths. 72 minus 34. 72 minus 32 would be 40 plus 2 more, right? Or minus 2 more. Okay, so there's my x. So x ends up being this yucky number, negative 38 ninths. And y ends up being this yucky number. And so my solution to this system, move that up a little bit, my solution is x equals negative 38 ninths, and 34 ninths is where these two lines will cross. So go ahead and try the next page on your own. I'll be in classroom waiting for you if you have any questions or if you want to walk through any other ones. All right, good luck, you guys.